Hi, I hope everything's going well. We're in the seventh week, and I thought I would go backwards. It seems like I'm probably a little bit ahead of everybody, so my video will be the end of last week's lecture. It's about an exponential random variable. We did a uniform and a normal, and then this is the exponential. It has some nice properties. It's a very has a nice density function with just one parameter, lambda. So it's easy to integrate, easy to deal with, but it also has this property called the memoryless property. And that will pretty much come up in this first problem. The time between the first and second heart attacks for a certain group of people is exponential. So I'll let x equal time between heart attacks, and x is exponential. And we don't know, it doesn't tell us what the parameter is, so we'll just put lambda in here. I'm not sure what lambda is. 50% of those who have had a heart attack will have another one in the next 5 years. So probability x is less than or equal to 5 years is equal to 50%. What's the probability that the person who had one heart attack 5 years ago will not have another one in the next 5 years? So no matter what time we start at, when you look at an exponential, it's as if you're starting brand new. So whether this person, if we just look at this person brand new right now, we're asking, what's the probability? It's been, again, they had one heart attack. What's the probability they're not going to have another one in the next 5 years, which means what's the probability x is greater than 5 now? So no matter when you start, I mean, even if we looked at them in 2 years and they haven't had a heart attack, and we say what's the probability it's going to be another 5 years, it doesn't matter when we started. So the probability x is greater than 5 is equal to 1 minus the probability that x is less than or equal to 5, which is just 50%. So really there's not much to do in this problem except to realize that the memoryless property is going on for the exponential. So we had one 5 years ago. We'll have to, yeah, so even though they had one 5 years ago, what's the probability we're going to have to wait another 5 years? We're just asking what's the probability x is greater than 5. And we know this nice property up here about x because we were told in the problem. So that's the first one. I took that from the exercises in the textbook. Here's another one from the textbook. I changed a little bit because they just had, they didn't have numbers, they just had constants. And the first time you see an exponential example, it's hard enough just to gather what's going on. So, and also there's that nice relationship between an exponential and a Poisson that I can show you in this problem. Suppose that at an Italian restaurant, the time t in minutes between customers ordering is exponential. So t equals time between orders, and t is exponential with a lambda of 1/3. And the reason I know this is because the expected value of t is equal to 1 over lambda. Or if I know lambda, then I know the expected value is 1 over that. So it has that nice relationship there. So let me see, f of t, if I want to build a density function, is lambda, so 1/3 times exp to the negative t over 3, and this is valid for t's bigger than 0. Okay, so there's my function. If I want to find what's the probability time is more than 2 minutes, less than 1 minute, whatever I want to find, there's my density function that I would integrate. So let's highlight that. Let's look at this now as a Poisson. Poisson, x equals time, not time, but number of customers who order in 1 minute. Okay, so the time between orders is exponential with a mean of 3 minutes. So number of customers who order in 1 minute would be, the mean here is time between orders is 3 minutes. So number of customers who order in 1 minute would be third of customer per minute. Okay, I don't know, that's kind of bothering me. That's the expected number. So number of customers per minute equals third customer per minute. Time between orders, mean is 3 minutes. So let me think about this. If time between orders is mean, so there, yeah, okay, that makes sense. So that means one customer orders every 3 minutes. So that means there's only a third of a customer ordering per minute. Okay, I know that sounds a little bit strange, but I need to figure out what the parameter is for the Poisson. So then the Poisson, P of x, it's a density function, it's a mass function, it's discrete. X is the number of customers who order in 1 minute. We expect a third of customers, so this would be 1/3 raised to the x times exp the negative 1/3 divided by x factorial, and this is valid for x's from 0, 1, 2 to infinity. Okay, so now I can look at the problem either way. Part A, I can do it as a exponential or I can do it as a Poisson. So let's just do part A. Let's bring up there we go. So what's the probability that no customer orders pizza during the next 5 minutes? So time between orders, that would mean the time between orders is more than 5 minutes. So let's find probability T is greater than 5. So I'm working with the exponential. I would integrate because it's continuous. So we integrate the exponential. 1/3 times exp negative t divided by 3. T equals 5 to infinity. And we're going to get something with an e, right? I should have done eval f or something. Eval f 0.189. Okay, so this is equivalent to asking no customers in 5 minutes. So the number of customers who order in 1 minute is a third of a customer. If we let y equal number of customers who order in 5 minutes, we expect 5/3 of a customer per 5 minutes. Okay, so what's the probability? So down here we're trying to find probability that y equals 0, where y is Poisson, where we expect 5/3 of a customer per 5 minutes. So now I'm going to sum. Let me see, this is Poisson with parameter 5/3. 5/3 the x times exp the negative 5/3 divided by, I probably should have stayed in y's, sorry about that, y factorial, y equals 0 to 0, no customers in 5 minutes. And we get the same thing. I don't know why I'm evaluating it again, we get the same value. So I hope that makes sense. For Poissons and exponentials, there's this nice property where you can go back and forth and rewrite it either way. I think there's a homework problem in 6 where I think I gave it to you as an exponential, and I don't know, I had to convert it back to Poisson to think about it. So sometimes one way or the other seems more clear to me. It kind of depends on the problem. Part B, what's the probability the next pizza order is placed in at least 2 minutes but no later than 6 minutes? I think this is easiest as an exponential. Probability of the time is between 2 and 6 minutes. So going back up here, integrate f of t 1/3 times exp negative t divided by 3 from t equals 2 to 6. What's the probability of time between the next orders? Between 2 and 6 minutes. Again, I didn't think about that, so about 38%. Okay, so I hope that helps. I mean, I hope the memoryless idea is coming through. You could say, what's the probability that a customer, let me see, that the wait time is more than 10 minutes, given it's already been more than 3 minutes. This is just the probability of finding the time is more than 7 minutes, because the exponential doesn't remember that you've already been waiting 3 minutes. It's really just asking, I know I've been waiting 3 minutes, what's the probability it's going to take more than 10? That's really just an additional 7 minutes. So that's what the memory is. It's as if you're starting fresh, because it doesn't know you've waited there already 3 minutes. So that's what I mean by the memoryless property. And if you need another example on this, please let me know, and I'll do some others, because that connection between the exponential and Poisson is a little bit tough.